Hello and welcome to this session on implementation of time series with R. This is the second part of a two-part series about time series data. In the first video, we saw what exactly time series data is all about, and in this video, we are going to implement it in R. Before we do that, let's do a quick recap of what we did in part 1 of this video, and we will then move into the implementation. So we talked about what is time series. We did an introduction to time series in part 1, and we saw that time series is a sequence of data that is recorded at regular intervals. Could be daily, monthly, weekly, whatever. And needless to say, the data is time dependent. And then we have some historical data. Based on this historical data, we try to predict or forecast some future values. And we also saw that time series data has these 4 components. There is a trend, then there is seasonality, cyclicity, and randomness or irregularity. And we also talked about stationarity of time series data, because before we do any time series analysis, we need to make the data stationary, and the 3 components that are responsible for stationarity are mean, variance, and covariance. This is how a stationary time series data would look. If we plot a time series data, and if we plot the mean of a time series data, that would be constant like this. If it is stationary, if it is non-stationary, then it would be changing. And we also talked about how to find the moving average, the concept of moving average, how to calculate the moving average, and also in order to get a smoothen the whole thing, we talked about the centered moving average. And this is how, if we plot and visualize, this is how the data would look. This blue color is the actual data, and then the green color is the centered moving average, and the red color is the red colored graph, or the line are the predicted values. So with that recap, let's go ahead and implement a time series forecast in R. So in this section, what are we going to do? We are going to use ARIMA model. There are different models and algorithms for performing time series forecasts. So we will use ARIMA, which is the most common one. And we will also talk about what is autocorrelation and partial autocorrelation. And we will see that in RStudio as well. And then we will take you through a use case where we will forecast the air ticket sales for the future. And then we will end with the model validation using the Ljung-Box text. Okay, so with that, let's get started. First of all, as I mentioned, we will be using the ARIMA model to do the forecast of this time series data. So let us try to understand what is ARIMA model. So ARIMA is actually an acronym. It stands for Autoregressive Integrated Moving Average. So that is what is ARIMA model. And it is specified by 3 parameters, which is P, D, and Q. P stands for autoregressive. So let me just mark this. So there are 3 components here: autoregressive, integrated, moving average. Okay. So these 3 parameters correspond to those 3 components. So the P stands for autoregressive, D for integrated, and Q for moving average. So let us see what exactly this is. So these 3 factors are: P is the number of autoregressive terms, or AR. We will see that in a little bit. And D is how many levels of differences that we need to do, or differentiation we need to do. And Q is the number of lagged forecast errors. So we'll see what exactly each of these are. So AR is the number of autoregressive terms, and which is basically denoted by the P. And then we have D, which is for the number of times it has to be differentiated. And then we have Q, which is for the moving average. So what exactly AR terms? So in terms of the regression model, autoregressive components refer to the prior values of the current value. Well, what we mean by that is, here when we talk about time series data, focus on the fact that there is regression. So what exactly happens in regression? We try to do something like, if it is simple linear regression, we do some equation like y is equal to mx plus c, where there are 2 variables. One is the dependent variable and then there is an independent variable. Let me just complete this equation as well, mx plus c. Right? So this is a normal regression curve or a simple regression curve. Now here we are talking about auto-regression or auto-regressive. So auto-regressive, as the name suggests, is regression of itself. So which means that here you have only one variable, which is your maybe the cost of the flights or whatever it is, right? And the other variable is basically time dependent, and therefore the value at any given time, and that we will denote as yt, for example. So there is no x here, there is only one variable and which is y, and we say yt, which is basically the predicted value at a time interval t, for example, is dependent on the previous value. So for example, there may be a1 and then yt minus 1, and then there will be like plus a2 and right plus a2 and yt minus 2 and all right, and then plus a3 into yt minus 3. Alright, so basically here what we are saying is there's only one variable here, but there is a regression component. So we are doing a regression on itself. So that's how the term auto regression comes into play. So only thing is that it is dependent on the previous time values. So there is a lag, let's say this is the first lag, second lag, third lag, and so on. So the current value, which is yt, is dependent on the previous time lag values. So that is what is auto regression component. So this is what is shown here. For example, in this case, instead of y, we are calling it as x. So that's the same, and this is represented by some equation of that sort depending on how many lags we take. So that is the AR component, and the term P is basically determines how many lags we are considering. So that's the term P for. Now what is D? D is the degree of differencing. So here differencing is like for the non-seasonal differences, right? So for example, if you take the values like this, which are given for 5, 4, 6 and so on and so forth, if you take the differencing of one after another, like for example 5 minus 4 or 4 minus 5, the next value with the previous value, so 4 minus 5. So this is known as the first order differencing. So the result is minus 1. Similarly, 6 minus 4 is 2. 7 minus 6 is 1. So this is first order differencing, and here we call it as D is equal to 1. Okay, and same way we can have second order, third order, and so on. Then the last one is Q. Q is the actually we call it moving average, but in reality it is actually the error of the model. So we also sometimes represent as ET. Alright, so now ARIMA model works on the assumption that the data is stationary, which means that the trend and seasonality of the data has been removed. That is correct. Okay, so this we have discussed in the first part, what exactly is stationary data and how do we remove the non-stationary part of it. Now, in order to test whether the data is stationary or not, there are two important components that are considered. One is the autocorrelation function and the other is the partial autocorrelation function. So this is referred to as ACF and PACF. Right. So what is autocorrelation and what is the definition? Autocorrelation is basically the similarity between values of a same variable across observations, as the name suggests. Now, how do we actually find the autocorrelation function, the value, right? So this is basically done by plotting, and autocorrelation function also tells you how correlated points are with each other based on how many time steps they are separated by and so on. That is basically the time lag that we were talking about, and it is also used to determine how past and future data points are related. And the value of the autocorrelation function can vary from -1 to 1. So if we plot, this is how it would look. Autocorrelation function would look somewhat like this, and there is actually a readily available function in R, so we will see that, and you can use that to plot your autocorrelation function. Okay, so that is ACF, and we will see that in our R studio in a little bit. And similarly, you have partial autocorrelation function. So partial autocorrelation function is the degree of association between two variables while adjusting the effect of one or more additional variables. So this again can be measured and it can also be plotted, and its value once again can go from -1 to 1, and it gives the partial correlation of time series with its own lagged values. So lag again we have discussed in the previous couple of slides. This is how a PSEF plot would look in RStudio. We will see that as well, and once we get into the RStudio. And with that, let's get into RStudio and take a look at our use case. Before we go into the code, let's just quickly understand what exactly is the objective of this use case. So we are going to predict some values or forecast some values, and we have the data of the airline ticket sales of the previous years, and now we will try to find or predict or forecast the values for the future years. All right, so we will basically identify the time series components like trend, seasonality, and random behavior. We will actually visualize this in RStudio, and then we will actually forecast the values based on the past values or history data, historical data. So these are the steps that we follow. We will see in RStudio in a little bit. Just quickly, let's go through what are the steps. We load the data, and it is a time series data. If we try to find out what class it belongs to, the data is actually air passengers data that is already comes preloaded with RStudio. So we will be using that, and we can take a look at the data, and then what is the starting point, what is the end point. So these are all functions that are readily available we'll be using, and then what is the frequency. So it's basically the frequency is 12, which is like yearly data, right? So every month the data has been collected, so for each year it is 12. And then we can check for any missing values if there are any, and then we can take a look at summary of the data. This is what we do in exploratory data analysis, and then we can plot the data, visualize the data, how it is looking, and we will see how the data has some trend, seasonality, and so on and so forth. All right, then we can take a look at the cycle of the data using the cycle function, and we can see that it is every month. That's the cycle. End of every 12 months a new cycle begins. So each month of the year is the data is available. Then we can do box plots to see for each month how the data is varying over the various 10 or 12 years that we will be looking at this data. And from exploratory data analysis, we can identify that there is a trend, there is a seasonality component, and how the seasonality component varies also we can see from the box plots. And we can decompose the data. We can use the decompose function rather to see the various components like the seasonality, trend, and the irregularity part. Okay, so we will see all of this in RStudio. This is how they will look. This is the once you decompose, and this is how you will actually you can visualize the data. This is the actual data, and this is the trend. As you can see, it's going upwards. This is the seasonal component, and this is your random or irregularity, right? So we call it irregularity, or we can also call it random, as you can see here. Yes, so the data must have a constant variance and mean, which means that it is stationary before we start any analysis, time series analysis. And so basically, yeah, if it is stationary, only then it is easy to model the data, perform time series analysis. So we can then go ahead and fit the model. As we discussed earlier, we'll be using ARIMA model. There are some techniques to find out what should be the parameters. So we will see that when we go into RStudio. So the auto ARIMA function basically tells us what should be the parameters, right? So these parameters are the P, D, and Q that we talked about. That's what is being shown here. So if we use auto ARIMA, it will basically take all possible values of this P, D, Q, these parameters, and it will find out what is the best value, and then it will recommend. So that is the advantage of using auto ARIMA. All right, so like in this case, it will tell us if we use this parameter trace, we set the parameter trace is equal to true, then it will basically tell us what is the value of this AIC, which has to be minimum. So the lower the value, the better. So for each of these combinations of P, D, and Q, it will give us the values here, and then it will recommend to us which is the best model. Okay, because whichever has the lowest value of this AIC, it will recommend that as our best PDQ values. So once we have that, we can see that we can potentially get a model or the equation. Model is nothing but the equation, and based on the parameters that we get. And we can do some diagnostics, we can do some plotting to see whether there is a plot for the residuals, so which shows the stationarity, and then we can also take a look at the ACF and PACF. We can plot the ACF and PACF, and then we can do some forecasting for the future years. So in this case we have up to 1960, and then we can see how we can forecast for the next 10 years, which is 1970, up to 1970. And once we have done this, can we validate this model? Yes, definitely we can validate this model. And to validate the findings, we use Ljung-Box test, and this is how you just call box.test, and then you pass these parameters, and you will get the values that will be returned, which will tell us whether how accurate this model is, how accurate the predictions are. So the values of P are quite insignificant in this case. We will see that, and that also indicates that our model is free of autocorrelation, and that will basically be it. So let's go back and into our RStudio and go through these steps in real time. So we have to import this library. Forecast package is not installed. You have to go here and install the forecast package. Okay, so that's the easy way to install rather than, so click on this install. I will not do it now because I've already installed. So the first time, that's only one time. Then after that you just have to load it into memory and then keep going. So we will load this data called air passengers. So by calling this data method, and if you see the data air passengers is loaded here, and if we check for the class, it is a time series data, TS data. So we can check for the dates. We can also view the data in a little bit, and the start date is 1949 and January, and our end date is 1960 December, and the frequency is 12, which is like collected monthly. So that is the frequency, which is 12 here, and then we check if there are any missing values. There are no missing values, and then we take a look at the summary of the data. This is all exploratory data analysis, and then if you just display the data, this is how it looks. And then we need to decompose this data, so we will kind of store this in an object TS data, and then use that to decompose and store the new values. So let me just clear this for now. And if we decompose, basically as we have seen in the slides, decomposing is breaking it into the trend, seasonality, and irregular or random components. Then you can go ahead and plot it. So when you plot it, you can see here, let me zoom this. This is our original plot, or observed value as it is known as. Then we have decomposed the three parts, which is basically the trend. As you can see, there is an upward trend. Then the seasonal component. So this is some regularly occurring pattern. And then there is a random value, which is basically you cannot really give any equation or function or anything like that. So that's what this plotting has done. And then you can actually plot them individually as well. So these are the individual plots for the trend, for the seasonal component, and the random component. All right. So now let's take a look at the original data and see how the trend is in a way. So if we do this linear regression line, it will show that it is going upwards. And we can also take a look at the cycle that are there, which is nothing but we have a frequency of 12, right? So the cycles will display that it is January, February to December, and then back to January, February, and so on and so forth. And if we do box plots for the monthly data, you will see that for each of the months, right, and over the 10 years that the data that we have, we will see that there is a certain pattern, right? This is also in a way to find the seasonality component. So while January, February sales are relatively low, around July, August, the sales pick up. So especially in July, I think the sales are the highest, and this seems to be happening pretty much every year, right? So this is every year in July, there seems to be a peak in the sales, and then it goes down and slightly higher in December and so on. So that is again part of our exploratory data analysis. And once again, let's just plot the data. Now, as I said, in order to fit into an ARIMA model, we need the values of P, D, and Q. Now, one way of doing it is, there are multiple ways actually of doing it. The earlier method of doing it was you draw saw the autocorrelation function plot and then partial autocorrelation function plot, and then observe that and where does this change, and then identify what should be the values of P and Q and so on. Now R really has a very beautiful method which we can use to avoid all that manual process that we used to do earlier. So what R will do is, there is a method called auto ARIMA, and if we just call this auto ARIMA method, and it will basically go and test the ARIMA model for all possible values of this parameters PDQ, and then it will suggest to you what should be the best model, and it will return that best model with the right values of PD and Q. So we as data scientists don't have to do any manual, trial and error kind of stuff. Okay, so we got the model now, and this is the model. It has PDQ values are 211 PDQ, and this is the seasonal part of it, so we can ignore it for now. And so if we want to actually understand how that has returned these values 211 as the best one, there is another functionality or feature where we can use this trace function or trace parameter. So if you pass to auto ARIMA the trace parameter, what it will do is it will show you how it is doing this calculation. What is the value of the AIC? Basically, AIC is what defines the accuracy of the model. The lower the better. Okay, so for each combination of PDQ, it will show us the value of AIC. So let's run it instead of me talking so much. Let's run this. If we run auto ARIMA with trace, you see here there is a red mark here. That means it is performing. It's executing this, and here we see the display, right? So it starts with certain values of PDQ, and then it finds that value is too high, so it starts with again with some 0, 1, 1, 0 and so on and so forth, and ultimately it tells us, okay, this is our best model. You see here, so it says this is our best model 211. Let's go back and see, did we get the same one? Yes, we got the same one when we ran without trace as well, right? Now why is 211? Let us see, where is 211? Here is our 211, and if you compare the values, you see that 1017 is pretty much the lowest value, and therefore it is saying this is our best model. All other values are higher. So that's how you kind of get your model. And now that you have your model, what you have to do, you need to predict the values, right? So before that, let us just do some test of these values. So for that, you install T-series. Again, if you are doing it for the first time, you would rather use this package and install and say T-series and install it. And then you just use this library function to load it into your memory. Alright, so now that we got our model using auto ARIMA, let us go ahead and forecast and also test the model and also plot the ACF and PSCF. Remember, we talked about this, but we did not really use it. We don't have to use that, but at least we will visualize it. And for some of the stuff, we may need this T-series library. So if you are doing this for the first time, you may have to install it. And my recommendation is, don't use it in the code. You go here and install T-series. And I will not do it now because I have already installed it, but this is a preferred method. And once you install it, you just load it using this libraries function, and then you can plot your residuals, and this is how the residuals look, and you can plot your ACF and PSCF. Okay, so this is how your PSCF looks, and this is how your ACF looks. For now, there is really nothing else we need to do with ACF and PSCF. This is just to visualize how it looks. But as I mentioned earlier, we were actually using these visualizations or these graphs to identify the values of P, D, and Q. And how that was done, it's out of scope of this video, so we will leave it at that. And then we will forecast for the next 10 years. How do we forecast that? So we call forecast, and we pass the model, and we pass what is the level of accuracy that you need, which is 95%, and for how many periods, right? So basically we want for 10 years, which is like 10 into 12 time periods. So that's what we are doing here. And now we can plot the forecast value. So you see, this is the original value up to, I think, 62 or whatever, and then it goes up to 72. This blue color is the predicted value. Let's go and zoom it up so that we can see it better. So from here onwards we are forecasting, and you can see that it looks like our model has kind of learned the pattern, and this pattern looks very similar to what we see in the actual data. Now, how do we test our model? So we can do what is known as a box test, and we pass our model here, residuals basically, with different lags, and from those values here, the p-values here, we find that they are reasonably low, the p-values, which means our model is fairly accurate. Okay, great. So I hope this was helpful, and with this we come to the end of this video. Alright, so with that we pretty much come to the end of this video, and quick summary, we talked about what is ARIMA model, what are AR and the D, which is for the degree of difference, and moving average. So the PDQ values we talked about, we briefly touched upon autocorrelation function and partial autocorrelation function, and we saw that in R as well. We plotted and saw it in R. We saw how to implement this in RStudio, and as a part of that we did some exploratory data analysis, and then we did the time series decomposition, and then finally we did the forecast, and then we kind of validated the model as well. With that, we come to the end of this video. I hope you enjoyed this. Thank you very much once again for joining. And if you have any comments or questions, please put it at the bottom of the video, and preferably with some contact information so that we can get back to you. And you have a great day. Thank you once again. Bye-bye.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.